Section 2.6, the last of Chapter 1, Equivalence Relations. Really, I assume you've already seen this, so I'm just going to do this pretty quickly and mostly in a reviewing way. Obviously, you can read the text and go over it carefully if you need to. All right, remember, an equivalence relation is just a relation on a set that satisfies three properties. The first is that A is always equivalent to A. The second is when A is equivalent to B, B is equivalent to C. Then by transitivity, you get A is equivalent to C. And the third is that when A is equivalent to B, then B is equivalent to A. Now, mostly, this chapter has been studying a very specific type of equivalence relation on the integers, namely mod n. And we've seen that this is indeed an equivalence relation, that saying two things are equivalent when they're congruent mod n is a specific type of equivalence relation. Now, as a definition, one of the early things we did with modular arithmetic and that particular type of an equivalence relation was to define congruence classes. We're going to do the same thing with any equivalence relation, and this will come up a lot throughout this whole course, different types of equivalence relations. And instead of calling them congruence relations, we're going to call them equivalence classes, but it's the same idea. So here's the definition. All right, we have a set S and an equivalence relation on it. Number one, given an element A, the equivalence class of A, written with square brackets around it, is the set of all B's that are equivalent to it. This is the same definition we had for a congruence class, where we looked at everything that was congruent to A. But for a general equivalence class, just everything that is equivalent to it. Number two, whenever you have an equivalence class and it's the square bracket of some A, everything equivalent to A, we say that A is a representative of A. And just as before with modular arithmetic, the representative is almost never unique. Alrighty, number three. The set of equivalence classes is called S mod tilde, where tilde is the equivalence relation. As we've said, our main example so far, our only example, is the set congruence classes. So if you start with the set being the integers and your equivalence relation being congruence mod n, then the thing we called Zn is really just Z mod this equivalence relation. So Zn in different notation is written Z mod this equivalence relation, the equivalence relation of congruence mod n. All right, we proved a theorem about congruence mod n, and that proof carries over almost verbatim to any type of equivalence relation. And there were three main parts of it. I'm just going to state it. We won't prove it here. It should either be trivial to prove, or if not, come see me. All right, number one. So two equivalence classes are equal exactly when their representatives are equivalent. Number two, two equivalence classes, remember they're sets, subsets of S. They're either identical with different representatives, of course, or they don't meet at all. They're disjoint. Number three. So S is the disjoint union of its equivalence classes. Another way to say that is the equivalence classes partition S. They break it up into a bunch of subsets. Anyway, that's everything there is to say on section 2.6.